Hello. In today's discussion, we are going to continue to discuss Fourier series and develop an actual Fourier series. So do the full-blown derivation of a Fourier series for a triangular waveform. And then we'll also show some MATLAB stuff to kind of see or hopefully prove that our approach for Fourier series is valid. And then present a little bit of where we can do some simplifications where we have developed a table. So very similar to what we did with Laplace, where we did a lot of derivations, and we're going to go ahead and do some tables for some typical waveforms to hopefully make our life a little bit easier. I'm not expecting you to do the derivations. I'm just doing the math so that you can see where this comes from, and then hopefully doing enough plots to where you can get pretty comfortable with the work so that you can say, yes, this actually is a valid approach to recreating a periodic waveform. So let's begin. So we are looking at a couple of alternative waves to represent the sine cosine form or the trig form for our Fourier series. And here's another one. It doesn't matter where you integrate, what period. You can see this is 0 to t, and our DC value is 1 over period. It's basically the same thing. As long as you integrate over one period, this approach is perfectly fine. So it's still multiplying our original functions and integrating over the period. So we're getting an, the cosine terms we have to integrate by, and notice we have omega sub 0 or omega sub 1, I'm sorry, which is the fundamental frequency. And then n is our integer multiple of that. Since it's a time domain function, we have to include the t. And then we have the ft. We do the same thing for v sub n, but we're multiplying it by sine to get that value. And recall where we had a trig identity when we multiplied two functions together, two sines or two cosines together. When we integrate over one period, all we're left with is the DC. So everything else gets filtered out by doing this approach. So let's look at a triangular waveform. And it starts at 2 and goes to -2. And you can see it repeats after every 1 second. It has a negative slope up until 0.5. And then from 0.5 to 1, it has a positive slope. So one of the things that we're going to have to do is we're going to have to figure out the process, which is determine if it's periodic, determining if it's if it has any DC offset, and also determining what the actual waveform equations look like, because we somehow have to go ahead and integrate those out to get what those values need to be. So we're going to have to define expressions for our f of t that meets this criteria. So the first thing is it periodic? And the answer is it appears to be periodic because it seems to repeat every 1 second. We only show the first 2 cycles, but we're going to assume that it continues on indefinitely. So after 1 second, it repeats. So yes, it is a waveform. So the next question is, if it's a sinusoidal waveform or a cosine waveform, and if it's a pure sine or a pure cosine, we really don't have to do any Fourier series because it already is set up in a sine or a cosine form. So you don't have to do any work if it looks like a sine. You know what the coefficient is. It's basically given to you. But in this case, it doesn't look like a sine wave at all. It's a triangular waveform. So we've got to go ahead and do a Fourier series to look at the relative power levels for this. So now we're going to find the fundamental frequency, that omega sub 0, or we could call that omega sub 1. That's in the expression. So either one is fine. It just shows that that's the initial or the fundamental frequency. So you can substitute the 1 or the 0 in here. But we integrate our sine or our cosine are always going to do in radians per second. So when we multiply the radians per second by second, then we get omega. So we only take sines of or cosines of a radian or a degree. So that's why we can't just put directly f in there. We have to put omega in there, or omega sub naught in this case. So omega sub naught or omega sub 1, in this case, is just 2 pi radians. Radians per second, sorry. All right, so now we're going to solve for the coefficients. We don't have to worry about a sub 0. A sub 0 is definitely going to be 0 because we see that the area of the axis or the area of the waveform above the axis is equal to the area of the axis below, or the area of the waveform that's below the axis. So you could certainly do the approach to solve for a sub 0, but this is a case where you can recognize that perhaps there's some efficiencies in this work. And what you do is you just simply state that my a sub 0 value is equal to 0. If you want to go ahead and check and do the integration, you're welcome to do that. We'll see that how to get that in a minute, but it's actually not too hard of an integration. But we can lay that out in a little bit. Now we're going to solve for a sub n. and b sub n. But again, we need those f of t's to be able to do that. So we have to define those. So they're just two lines, they're two straight lines. So we can use y equals mx plus b to solve for the lines and what those equations are between our first, for our first period, which is between 0 and 0.5, and then our second, which is between 0.5 and 1. So we're not necessarily going to do that here, but I encourage you, if you want to take a look, you can look at the y-intercept to figure out the b value, and then you can get the change in y over the change in x to get the slope value. So for our first one, which is between 0 and 0.5, where we had the negative slope, we have negative 8t plus 2 is the expression. And then when we have the positive slope, which is between 0.5 and 1, we have 8t minus 6. And you'll notice that I have, let's see if I can mark it up this way. Hopefully this is, oops, that didn't work so well that way. But what we see right here is we go from less than or equal to 0 here, but we stop it at 0.5 because we don't want this expression to live at 2 points. But we'll take care of that in the integration limits. We'll just essentially set them equal to 0 or equal to each other. But we can see that we have those terms there. But when we do the integration limits, we say that it's essentially going to be the same point. So now we'll solve for the coefficients. And what I would do is, if you take these two expressions here, the f of t that you see here, and you integrate it to get the dc term here. So you integrate that over one period, you would put those two terms in there. So you go from 0 to 0.5 for the minus 8t and the 0.5 to 1 for the plus 8t. And then you put that in parentheses, you divide by the period, which is just equal to 1 second. You would evaluate that is equal to 0. But again, you can check to see that hopefully this area plus this area here is equal to that area. So the positive areas are equal to the negative areas, so there's no DC. All right, so let's begin. So this one's going to be a little bit of a math one, but hopefully it doesn't get overwhelming to you. We have all the steps here. And again, I'm not expecting you to do this. I'm just showing you the process for how you would actually solve this particular problem. So we'll solve for a sub n. We'll put our 2 over 1, which is the multiple, that 1 over the period. And then we're going to integrate. We'll have to have two integrations because we have two separate equations for f of t. The first f of t equation is right here, and that's the cosine of 2 pi n times t. This here is the omega 1 or the omega naught. And then we put the second one here. Now the integration limits are 0.5 to 1. And again, this is the f of t where that exists. And we still put the cosine 2 pi and t here. This is that omega sub 1 term. All right, so now what we're going to do is we're going to break out the terms because it's a little bit easier integration if we don't have parentheses or multiplying things in there. And I'm also going to factor out the constant or move the constant out here because this one is just a constant. It's not affected by the integration at all. So I have 2, then I have my minus 8 over here. The t stays in here, and then I've got my cosine 2 pi n t dt over here. Then the 2 comes out over here, and again, that's just a multiple of a constant. So I have my cosine 2 pi nt dt over here. I do the same thing for this one by breaking it out, and this one becomes plus 8 t cosine 2 pi nt dt, and minus 6, again over here, cosine 2 pi nt dt. So the only difference that I have in these integrals is the limits here. You can see that these limits are different, and obviously the expressions are slightly different as well. Now, hopefully what you're starting to see is that there is some helpful information. And the helpful information that I see here is this is a pretty straightforward integration, as is this one. That's just the integral of a cosine of something with respect, or something times time dt. So those two integration limits are extremely easy to do. So we'll do those first. We'll do the 2 term first. So 2 times the cosine 2 pi nt dt, 2 over 2 pi sine 2 pi nt dt. So that's when you use the chain rule to get that value. And then we have our integration limits there from 0 to 0.5. Now we're going to go ahead and actually integrate what the limits are. So you can see that my 2's will cancel over here. I'm left with 1 over pi times n. Then I have the sine of 2 pi n. This is my upper limit value for t. And my lower limit value for t is equal to here. Now, this is where I have to start thinking a little bit about this in more detail. So this is sine pi n times 1. So pi n times 1, and then n starts off at 1. So when we talked about this the other day in class, the sine of pi is going to be equal to the sine of 180 degrees, and the sine of 180 degrees is equal to 0. The sine of 3 pi is going to be equal to 0 again. So that's 360 plus 180, it's 540, and on and on and on. So this is always going to evaluate to 0. This one's more obvious because the sine of 2 pi n times 0 is always going to be the sine of 0. And we so know that the sine of 0 is always equal to 0. So this is 1 over pi times n, 0 minus 0, regardless of the value of n. Okay. So this is when you have to spend a little bit of time thinking about how can I come up with some general terms to evaluate those expressions. So what I see is that I've got, no matter what the value of n is, I plug in 1, 3, or 2, 3, 4, 5, et cetera, et cetera. This is always going to be a multiple of pi, and an even multiple of pi or an odd multiple of pi, 1 pi, 2 pi, 3 pi, is always going to be equal to 0. So I'm taking into account that that's the case. You can always set up a table if you're not sure. So you could set up a table where you have n here, and then you have the sign here. Sorry, this is kind of hard to do with a mouse. You start off with 1, then 2, and then you do the evaluations over here, just like we did in class, and you'll see that those always are equal to 0. So if you're having a hard time seeing that, it's easy enough to go ahead and do this really quickly and see that those are always equal to 0. Let's do the same thing now for the next term, which is the minus 6 cosine 2 pi nt. So minus 6 is up front, no big deal. We're going to use the chain rule again. So minus 6 divided by 2 pi n, this becomes the sine, the integral of this becomes a sine of 2 pi nt. Now I'm going to evaluate the integration limits. Now I have 1 and 0.5, whereas before I had 0.5 and 0. So I'm going to substitute that in for t. So you just see that there's no value there because the t is equal to 1. So that's 2 pi n. And then my next one is 2 pi n times 0.5. So this is 1. So go back in and let's look at this one. Let's let n equal to 1. So 2 times pi times 1 is 2 pi. Sine of 360 degrees is the same thing as sine of 0. So this is equal to 0. Let's go to 2. 2 times pi times 2 is 4 pi, which is just 720 degrees. And again, that's equal to 0. So if you continue to increase it, this is always going to be equal to 0. And over here, we already did this one. We already proved that this is 0. So we can use that same concept to identify that that is going to be 0. So both of these terms are always equal to 0. So they actually add nothing to the expressions. They do not contribute in any way, shape, or form to my a sub n value. So those are pretty easy to integrate, but they're also pretty good because they don't actually contribute anything. So it makes our work a little bit easier. All right, so now let's go to our next step and do a little bit more difficult one. And so this first discussion over here is where we have the sine of pi is always equal to 0 regardless of the value. That's just sort of the more description, the discussion of it. So if you have more, if you need more discussion of it, you can include that here. Now we're going to go ahead and do the other terms, which are not necessarily easy integrals. Those are going to require integration by parts. And if you don't recall integration by parts, the reason why you do it is because there's a t over here and a t in here, and there's no way of combining those two to like a t cubed, for example, or an ln of t or anything like that. It's just impossible to add those, and you can't integrate those separately. So you need to use the integration by parts to do that. So I've given you what our integration by parts is going to be equal to. This is the integration by parts equation. If you don't recall it, I included it here. U dv equals uv minus integral of v du. Don't forget you have to integrate at the original limits that you had specified. I don't show those here. I just did it generically. So now I'm actually showing you what the expressions are going to be. So my dv, and this is just a general approach. Usually your dv is going to be the hardest one to sort of differentiate out. Like if I differentiate the cosine, then I end up with a sine, so it's never going to go away. So what I'll do is I'll specify the dv to be equal to this one and integrate it. And then this other term, I need to eventually get that out so that that no longer has the t term inside of it. So I set this to dv and t equal to d. Whoops, where am I? And sorry, this is dv, and then u is equal to t. So this is u dv. So I have my dv, my u. Now I just go ahead and do the expression. So v is the integral of this term. So sine 2 pi nt over 2 pi n. Again, using that chain rule. And the du is just the derivative of this. So du is equal to dt. That's a much easier way. So now I substitute into my original equation my udv here. So my uv here. So this is my u term right here. It's t. Ends up over here. This is u. This is that part right here. The -8 doesn't get factored in it because it multiplies the integral up front. It's just a constant. So it doesn't have anything to do with the evaluation. That's way up front. So I integrate between 0 and 0.5 because those are my original integration limits. When I integrate by parts, nothing changes. I continue to do the exact same approach to integrate by parts. I am continuing now. Now I have to do the integral of v du. So my v here is equal to this term right here. So that's the sine 2 pi nt. And I've already pulled out the 1 over 2 pi n because that has no t term in it. So I'm just setting it up a little bit so that you can actually start to see that this integral is very similar to the ones that we did on the previous slide. By putting this out front, and hopefully makes this a little bit more obvious that this is a pretty straightforward integral. And then my du is actually really important because it gives me some variable to integrate with respect to. So this is sine 2 pi nt, and it's almost exactly the same as we did before. So what I end up with is my term where I have this one that has to be integrated by at the limits, and then this one I have to continue the integration. So -8, this is the upper limit, 0.5 sine 2 pi n 0.5 divided by 2 pi n. This is the lower limit minus that value here, okay? Because I have the t out front, right? So that's where the t term ends up. That's why you have a 0.5 and a 0, and a 0.5 and a 0 over here. So those are the terms that are integrated. And then the last term I have here is the final integration that I needed. So you'll notice the inclusion of the integrals here. So this whole line laid out over here is the entire sort of integration at this point with all the terms evaluated for the limits. And notice there's no t over here. So you notice there's no 0.5 and 0 over here. It's just the cosine. Okay. All right. So I have all these terms. I've got them all ready to go do my limits. Now I'm going to go ahead and just kind of clean things up, which means I can take this term and throw it away because it's always multiplied by 0. So that term is never going to contribute anything. So -8 times 0.5 sine pi over n, 2 pi n, cosine 2 pi n, because these two will cancel over 2 pi n squared. And I also made a substitution over here, hopefully to make this a little bit easier. This is cosine 2 pi n times 0. So no matter what the value of n is, it's always going to be 0. So the cosine of 0 is 1. So I made this substitution in here to make it a little bit easier. You can also see that I could cancel out those 0.5 and the 2 over here, but I was just trying to make it so that you can hopefully see some of these terms. All right, so now I got a bunch of n terms in here and I got a bunch of different things. So I'm going to set up a table. And this is, again, a recommendation just so that you can hopefully see it a little bit easier. But I want to go ahead and I want to set up a value of n and see what happens to my sine of pi n and my cosine of pi n. Because if you notice over here, I have a sine of pi n and a cosine of pi n. So no matter what my value of n is, that's what this table says, this shows that this is always equal to 0. So for a more complicated evaluation that I'm trying to do, I'm actually going to show you the table so it's easier to follow. This is equal to 0. The cosine is -1, 1, -1, 1. Okay. So no matter what this is, this term always evaluates to 0. So this term drops out. This term does not drop out, but this is where I have to be careful because if I look over here, -1, 1, -1, 1. So carefully looking down, I see that this is a -1 over here. This denominator is the same. So when this cosine of pi over n or pi n evaluates to a +1, 1 minus 1 with the same denominator will cancel each other out. So looking closely, whenever there's a positive 1 here and here, those terms are going to evaluate to 0. So this is a pretty unique one. This is a case when I only will have one term left. This term will add to this term. So basically I will get double if n is an odd number. Okay. So the criteria here is that I will get two of these because I have a minus 1 and a minus 1 here. So I'll have minus 2 over 2 pi n squared if and only if n is an odd number. Okay. That's pretty important. So it's odd and 1 when n is even. So I'm going to go ahead and say that here's my value. So minus 1, you can see those terms over here. I've got the minus 8 up front. That's going to give me 4 because I've just divided out the 2 term over here to simplify it a little bit. And a sub n only exists and is only equal to this value when it's 4, or is equal to 4 over pi n squared when n is an odd number. If n is an even number, so if this is an even harmonic, it's always equal to 0. It never exists. So that's the one that I've got 3 of the terms that I went back through over here. So here are my terms. I've got, oops, right over here. I've got this term. So let me erase some of this stuff. Just erase this. And I've already done this term. That term we determined was 0. That term we determined was 0. We did this term and we said this only exists if n is odd. Sorry, I'm doing this with a mouse, so it's pretty ugly. So we have that term, and that only exists when n is odd. If we can prove or do the same approach for this term over here, because we haven't done this one yet, if this, not this term, sorry, I skipped a term. Let me do that again. Let's do this term. So this one is done. So this term I have to do. So if I can prove that this term only exists when n is odd, then I'm in pretty good shape. And I can't categorically say that because the integration limits are off. So even though it looks like the same thing, I can't say, yes, this is applicable until I actually do the integration there. So let's go ahead. And what we went up with is we do another integration by parts. And we can find the other term. And the other term is going to be exactly the same. And it only exists when n is odd. So if you want the practice for how to get that, you can go ahead and instead of having, let me go back over here. So instead of having this expression over here, you put in the 6, and then you put the 0.5 and 1 and do the exact same process, and you'll end up with another term here. So what this tells me is that my a sub n is going to be equal to 16 over pi n, that quantity squared, when n is an odd number. So that is the second term. We found a sub 0, which is equal to 0. We determined a sub 1 is going to be equal to this. Now we have to solve for the b sub n term. And I'm not going to do that here. It's a lot of math, but what we're seeing is it's going to give you the exact same result, and they're always equal to 0. So how do I represent this Fourier series, representation? Pretty straightforward. My f of t is 16 over pi squared. N equals 1 to infinity. And notice I had to move the n out front over here because it's part of the summation. So if I go over here, it's 16 pi over n squared. I moved the 16 pi squared out because it doesn't have the value n, but I had to keep that over here because the n value will change. And here's the value that we have here. Now, this is interesting because it shows that as n is increased, the n squared term goes up, which is dividing the cosine term. So at higher and higher frequencies, this is going to contribute far less of the power. So most of the power in this one is going to be at the fundamental frequency, and then it's going to decay off very quickly. All right, so here's a couple of cases where we have some harmonics. We have n equals 1, n equals 3. I'm going to go ahead and bring up a MATLAB script file that I wrote. And this is the script file that shows that we have a bunch of different terms. So we're going to go ahead and just do this first one here, where we're going to run the plot, and it's only going to do f of 1. So this is just doing where n is equal to 1. You can see there's no n term in here. It is in there. It's n squared, which is 1 squared. And then we're going to plot that. So we're going to run that to this point, and we're going to plot it. And where did that go up? Here we go. And that's the term that we have here. So doesn't look anything like a triangular waveform, but you can clearly see it looks like a cosine waveform. Its peak value is almost 2, but it's not there. And its negative peak value is almost -2, but it's not there. So let's continue on. Let's continue to step through this function and add in another harmonic. So now you can see that I have n in here. I put n, which is pi3. This is 2 pi times n. So this is just 2 pi times whatever frequency I'm evaluating. So let's step through. Now I'm adding in the 3. So I put those two plots together, and you can see that this has triple the frequency that the original waveform has, but it has way less magnitude. So now in this step, I'm going to add those two together, and I'm going to see how this waveform is changing. So remember, looks like a cosine wave that's almost 2. This looks like a cosine wave that's pretty small at 3 times the frequency. And now we're going to plot it. So it's looking more like a triangular waveform. It's still kind of ugly, but it looks better than in the first case. So let's add the 5th harmonic. So again, you can see that n's equal to 5 right here, and I have 16 over pi n squared, and I get this value over here. So I'm going to go ahead and continue to do that. And I'm not going to bother plotting the 5th because you can't really see that much. I'm just going to display the total and do that right here. And now we're starting to get close to a triangular waveform. So looking better and better. And I only had to do 5 harmonics. So what I'd like to do is I'd like to set up a system where I can just automatically go and add harmonics in and see how that response changes based on those harmonics. So I set up a little loop here that this is my harmonic number. This is n. So I can set that to have the first harmonic, the 3rd harmonic, the 5th harmonic. I just specify what harmonic I wanted to go to. As long as it's an odd number, it's fine. And this NN is basically keeping track of all the harmonics there. So if I go to 1, it goes to 1, it skips 2 spots and then goes to n. So if n is 3, it goes 1 to 3. If it's 5, it goes 1, 3, 5. If it's 7, 1, 3, 5 to 7. So that's just a way of setting it up. And then I clear a bunch of stuff, basically clearing my plots. I clear my f variables, and then I just do a for loop, which basically does exactly the summation. It does my f. This just starts off with whatever value is for my n squared, and then here's my function, and then I just keep rinse and repeating. So we did 5. Let's change this to 7. I'm going to stop that. I'll clear all my breakpoints. I will run it. And then if you wait a second, this shows you, it's hard to see, but it's a slight improvement from 5. Not perfect, but a slight improvement. Let me go back to 5. Actually, let me do a screenshot of this. And perhaps we can do a comparison. Actually, we can do the comparison right here. This is the 5, and this is the 7. So if you look at what I have for 7, these two look exactly the same. So it's getting close to a value of peak for 2 and a minus peak for 2, and it's starting to get a little bit rippled here, but it's starting to straighten out. So let's add another one. Let's go to 9 and run it. So again, slight changes, and that's because if you look at the value for a sub n, it is so small. It's 16 divided by pi squared, divided by, at this point, this is 9 squared. So 16 divided by pi squared times 81 is a pretty small number. So to get this to be close, I'm going to have to start adding a lot of it. So instead of going to 9, let's go crazy and make it 99 and see how much closer this gets. Wow, look at that. With 99, it's almost a perfect triangular waveform. So all I did was add a bunch more in there, and I get almost exactly that original waveform. So let's go back and compare. Here's my original waveform, and I just drew this in pencil. And let's do the comparison for the waveform. And 2 down to minus 0.5, at 0.5, at minus 2, back up to 2 at 1. Looks pretty darn perfect. So this is with 99 harmonics, and that's quite a bit. I don't think you would probably in the real world go much past the 11th or the 13th harmonic, but this just gives you the option to go ahead and solve for that. So hopefully you found this MATLAB script file really helpful to see the addition of the harmonics and also to do the proof that, wow, I can add a bunch of cosine waveforms because that's what I'm doing in line 20. I just add all these cosine waveforms together. And if I have enough cosine waveforms together and do the calculation correctly, I can recreate a triangular waveform. All right, so let's go back to here, those waveform plots. And that was after 4 harmonics, but we also see that we can use some concepts of symmetry. We talked a little bit about even and odd functions. Well, we'll learn a little bit and we'll see that where if you have an odd function, you can see that there's only certain parameters in there, or if it's an even function. So we'll take a look at that. If you only have cosine terms like the one we just represented, you're going to have an f of t is equal to a0 plus divided by 2 plus the summation over there. This is called the Fourier cosine series, and it can only represent those terms where our b sub n term is. So that is going to be, and I'll pause and show you for a second because we saw that b sub n is 0. Let's get to that waveform. So over here, if we copy this function, we see that f of x equals f of minus x. So if you remember from the definition, that would be the odd function that we discussed way back at the beginning. So you can take a look and see that the v sub n terms will go away. So again, another way to save you some effort. The other thing that note too is in this case, you only have, we talked about the DC term being an A term and the B sub n term, not being associated with DC. Well, the reason being is because in these type of functions, when f of x equals f of minus x, you can have DC offset. So you can have an odd function where you have those two. If it's a function where f of x equals f of minus x, then you can't have a DC function. But that means that that is going to have a sine term. So this term is DC because the only time you're going to have a DC value is if there is a cosine function with it. If there's no cosine function with it, you can't have a DC. So that's why it's denoted as an A. It's not any more than to give you a little bit of a hint that you perhaps can have some DC associated with it. And then here's a sine term, and notice there's no DC. Those terms always cancel out to 0 because of the criteria about f of x equaling f of equaling minus f of x. All right, so the next step here is just kind of just a summary of how to make things easier. So what we're going to do is we're going to identify if a function is even or odd in a given function. If it's an even function, we're only going to calculate a sub 0 and a sub n, and then write the cosine Fourier series. If it's an odd function, we're only going to calculate the b sub n term and write the sine Fourier series. And remember back from a few slides for the even and odd functions. Let's go back over here where we have the plots. Get there at some point. So even function, f of x equals f of minus x. Odd function, f of x equals minus f of x. I think I may have said that incorrectly. I apologize for saying that incorrectly. Even function, here's the definition. Odd function, here's the definition over here. All right, let's do one more slide, which is to show how to represent all this data, because we have a lot of math to do. But the question now is, all right, we have all this wonderful math and it looks like it works pretty cool, but what do we do with it? Well, in the real world, our applications are based on, I have a Fourier series, I know what the power levels that are, or I can calculate what the power levels are. Now the question is what to do with it. Well, the first thing I need to do is to display that information. How do I actually display that information? Well, the way you display it is a power plot, a power spectrum plot. You literally are just presenting what the power is and at this level. And so if you take a look at our term we just represented, the A sub n for the triangular waveform, our A sub n magnitude is 1.6 at the fundamental. It's 0 at the second harmonic. It's 0.2, so very little power, but still, a reasonable amount. And then it starts dropping off as we go to the 5th and the 7th. And if you continue on, we get very little power concentrations. So if you're deciding if a piece of equipment is experiencing a failure, you don't look at the fundamentals so much. You look at these other power levels and relative to the fundamental, how much power is in there. And that is a very useful thing for when you do spectral analysis, when you're looking at power levels to see how clean or messy a waveform or if a failure is imminent. And I'm going to end with this. So we saw the Fourier series. So this is just like Laplace. How to do some basic, simple sort of, if you will, some representation. So these are from a different book that has a derivation. We did this triangular waveform, and you can take a look and see that these only exist for the odd. You can see that this is 8a over pi squared, where we did 16, and that's because our a value was 2. It wasn't 1. This shows that this value would go to 1. So you just substitute a value in 2 in there, and you would get the original value that we developed. Okay. So you can see that this approach is what we just derived for our triangular waveform. And again, this function here is an even function. F of x equals f of minus x. So I only have the cosine terms. You'll also note that I do not necessarily have to have a DC expression in here. Okay. There's no DC in this waveform. And also in here, you can see f of x equals f of minus x. So there's only cosine terms in here, but there's no DC. So I don't have to have DC. Here's 2 expressions that show I don't have it. Same thing over the sawtooth. But if you look at this half-wave rectified, you can clearly see that there's no negative error over here. So you'll notice in this term, there is in fact a DC element in there. And the other terms beyond there do that. So if you don't want to do the math, and it's a lot of math to get from point A to point B, and I'm not expecting you to do that, you can just use these table to go ahead and set yourself up for that. So that's all I wanted to cover here. I went through it quite a bit because I wasn't able to do a live interaction, but I wanted to make sure that we had a class to talk about this concepts, and pretty much everything through this point would be something that perhaps you would see on the exam. So understanding how to do the spectral plots and doing all that. Here's an example for how to do all that. And we'll cover that when we get back in class, but this is the material that I wanted to present for us to be able to do that. So with that being said, I hope you enjoyed this presentation, and I look forward to talking with you soon. Take care and have a wonderful